In this video, we'll be solving the one-dimensional homogeneous heat equation. And the method that we're going to use to solve this, there are numerous methods, but the method that we're going to use is separation of variables. So, get the pen working, separation of variables. We're going to let u of xt equal capital X of x times capital T of t. Now the aim here is to sub this in to our equation and to separate the variables into two ordinary differential equations instead of a partial differential equation. Ordinary differential equations are much easier to solve, and so we'll be able to hopefully solve this. Okay, so before I substitute in, let's deal with our boundary conditions and our initial condition. So, u of 0t equals 0. So that means that x of 0 times t of t equals 0. But this holds for all t. So I can make the claim that x of 0 equals 0. And similarly, u of L t equals 0. So therefore x of L times t of t equals 0. But that's for all t. And so therefore x of L is equal to 0 as well. Okay. Now, let's see what we get. du on dt, so I'm differentiating the function with respect to t. So x, well, that's just a constant with respect to t, so that stays as it is, stays as x. But t, well, I take the first derivative, so it's t dash. Now, d2u on dx squared, well, x is not a constant, so x gets differentiated twice, but t is a constant, so we don't touch it, and it stays as it is. So now I can sub these back in to my partial differential equation, and I'll get the following. I'll get x times t dash equals to kappa times x double dash t, and I'm going to get all the t's on one side and all the x's on the other side. So in doing that, I'll be separating my variables. So I have dividing by t, and I'm going to also bring the kappa down as well. Kappa t, and then I'll divide by x, so I'll get x double dash on x. Now, here I have, in the left-hand side, something that is completely dependent on the variable t. And in the right-hand side, I have something that is completely dependent on the variable x. But the two of them are equal. So the only way that that can be is if this is equal to some constant I'll call k. And k is a constant. Let's just write that down. So once again, something that's completely dependent on the variable t is equal to something that's completely dependent on the variable x, and the only way that that can happen is if both are equal to a constant. And so then I will have two differential equations, two ordinary differential equations. T dash on kappa t equals k, which means that t dash equals kappa k t. And I'll also have that x double dash on x equals k, which means that x double dash minus kx is equal to 0. So now I have two ordinary differential equations, which hopefully if you're taking a partial differential equation course, you know how to integrate ordinary differential equations. I have two ordinary differential equations and I need to solve these. So let's consider this case here. Now look at this equation. We need to consider three cases for k. Case 1. If k is equal to lambda squared, I'm ensuring that k is positive. So I'm ensuring k is positive, and I'll just specify that lambda is also positive. So if that is the case, then I have x double dash minus lambda squared x equal to 0. Hopefully you know how to solve this, and the solution will be x of x is equal to a constant a, e to the lambda x, plus a constant b, e to the negative lambda x. Okay, and now we are going to use our conditions that we derived here. So we can't use these straight out. We had to put them into this form after our separation of variables in order to use them here. So x of 0 equals 0. Now subbing 0 into this gives me a plus b. So a plus b is 0, or in other words, a is equal to negative b. Okay, now what about x of L? X of L is also equal to 0. So that means that a, e to the lambda L. Now, a is minus b, or b is minus a, it's the same thing. So this is minus a, e to the minus lambda L, is equal to 0. I'm going to factor out an a, and multiply the whole equation by e to the lambda L. E to the 2 lambda L minus 1 is what I'm left with. Now, lambda is greater than 0, so it's not equal to 0. What is L? Well, L is the length of our rod. We're looking at a one-dimensional heat equation. So if we have a rod, the length of it is L, which is clearly non-zero, otherwise this question is quite pointless. L is greater than 0. Clearly 2 is greater than 0. So I have a product of positive numbers here. I'm taking the exponential of that, so that's going to be greater than 1. So this term here is non-zero, and so that means that a has to be equal to 0. So if a is equal to 0, well then b is equal to 0. So therefore b is also equal to 0, and I recover a trivial solution here, that x of x is 0, and so essentially the entire function is 0. So this is a trivial solution, and I've finished with this case. I no longer need to consider it. Alright, now our second case. Case 2. So we went with k greater than 0. That didn't work. Now what about if k is equal to 0? Well then, we're going to just have x double dash. Now it was x double dash minus kx, but k is 0, so it's x double dash minus 0 equals 0, or just simply x double dash equals 0. And then I can integrate twice. So x dash equals the integral of 0, which is some constant. Let me call that a. Integrating again, x, just simply x, is going to be ax plus b, where a and b are just some constants. And so let me now use my initial conditions again, or my boundary conditions rather, which were x of 0 equals 0, which means 0 equals a times 0 plus b, so it's just b. So b is equal to 0, so therefore I have x equals to ax, because b is 0. Now what about my other condition? X of L is equal to 0. Subbing that in, I get 0 equal to a times 0. Oh, sorry, a times L. But again, L is greater than 0, and so therefore it's non-zero, and so therefore the only thing that could make this statement true is that a is equal to 0. And so therefore, I once again recover a trivial solution, which we're not really interested in. So I need to consider the third case, the third and final case, that k is equal to negative lambda squared. Now, negative lambda squared is always going to be less than 0, and I can also say that lambda is greater than 0. That's not really that important. It could be less than 0, it could be greater than 0, but the main thing is that it's not equal to 0. Okay, continuing on. X double dash, it was minus kx, so it's going to be minus lambda squared, so that'll become plus lambda squared x equals 0. And now hopefully you're very comfortable with solving this kind of a problem of an ordinary differential equation. The solution will be x of x equal to a cos of lambda x plus b sine of lambda x. Alright, once again, I'm going to use my boundary conditions. X of 0 equals 0. So that means that a times cos of 0 is 1, so a times 1, plus b times sine of 0 is 0, so it's 0 here, is equal to 0. This term goes off to 0. This is a times 1 equals 0, so a is equal to 1. A is equal to 0. Okay, so what do I have? I have x of x equals b sine lambda x. We lose this term because a is equal to 0. Alright, our other condition, x of L equals 0, means that b sine of lambda L is equal to 0. Now here, we don't want b to be 0, because this is our final case, our final possibility of finding a solution. So b can't be 0, because if b is 0, then we have recovered another trivial solution. And so I've only got trivial solutions. I've only got u of x comma t is equal to 0, and that's really obvious, we're not looking for that. So I don't want b to be equal to 0. So the only way that this is non-trivial is if this is not 0, or in other words, this is 0. So I can say that therefore sine of lambda L should be 0 for non-trivial solution. Non-trivial solution. Okay, solving this, well, when is sine equal to 0? Sine looks something like this, and it's equal to 0 at integer multiples of pi. So 0, pi, 2 pi, 3 pi, and so on, for integer multiples of pi. So therefore lambda L equals n pi, where n is an integer, and therefore we're looking for values of lambda. So lambda equals n pi over L. And once again, I'll just say n is an integer, or I could say 0, 1, 2, etc. Dots. Actually, should not have 0, because lambda equaling, if n is 0, then lambda is 0, but we've already shown that lambda being 0 is not good enough, because if lambda is 0, then k is 0, and we show that that's a trivial solution. So really it should only be 1, 2, 3, 4, and so on. Okay, so I have these values for lambda equal to n pi on L, and these give us a solution. What's our solution? Well, our solution is going to be x of x equal to b. Now this is just a constant, but the constant is going to depend on what the value of lambda is, because there's different n's, so I can call it b sub n. So that's going to be sine of lambda L, but lambda is, of lambda x, but lambda is n pi on L, so I have n pi on Lx. Great. So now I've solved for half of my solution. Remember, when we separated, we had x of x times t of t. So now I need to solve the t ordinary differential equation, which is here. So I have t dash equal to k, or kappa, kt, but k is negative lambda squared, and lambda is n pi on L. So this is equal to minus kappa lambda squared, which is n pi on L all squared, times t. And this is just a very standard ordinary differential equation. It's first order. So the solution is going to be t of t equal to some constant, let's call it c, and it depends on the value of n. So let's say c of n, and that's times by the exponential of this coefficient of t. So minus kappa n squared pi squared on L squared t. Okay, now our solution was u of xt. U of xt was equal to x of x times t of t. Now I have all these, let me just say here, 1, 2, 3, and so on. I have multiple, actually I have infinite number of solutions for t of t and also for x of x. Now by the superposition principle, I can add all these solutions up. So my solution u of t is going to be the sum from n equals 1 because that's where I start, to infinity of, now it's going to be x of x, which is this thing here, times by t of t, which is this thing here. So I'll have b of n times c of n. Well, both of these are just constants, and they change with n. So I can call that one constant, a of n, times sine n pi on lx times e to the negative k, or negative kappa, n squared pi squared on L squared t. And this is almost my final solution. There's still one more bit that we need to do. Now, the final thing that we need is to evaluate what a of n, or a sub n, is equal to. And what we're going to use for that is our initial condition. U of x comma 0 equals f of x. So, if I substitute t equal to 0, well, u of x comma 0, where we just said was equal to f of x, and subbing t equals 0 into this would be n equal to 1, the sum from n equals 1 to infinity, a n sine of n pi on lx, and then this will be e to the 0, which is 1, and so this is what we have. Now, how can I extract this constant a n from this expression here? Well, we're going to use an orthogonality relationship. So, note that the integral from 0 to L of sine n pi on Lx multiplied by sine of m pi on Lx dx is equal to 0 when n is not equal to m, but when n is equal to m, it's equal to half the period. So L minus 0, which is L divided by 2. And this is a good exercise for you to work out for yourself, to actually do this integral and work out for yourself if you haven't seen it before. A similar one exists for cos. Alright, so how can I apply this thing here to my statement up here? Well, I'm going to multiply both sides here by sine of m pi on L, m for mother or something. So f of x times sine of m pi over Lx, and I'm going to integrate from 0 to L dx. Well, that should be equal to the integral from 0 to L, the sum from n equals 1 to infinity, an sine of n pi on L x sine of m pi on Lx dx. Alright, now without knowing what f of x is, we've just given a general function. There's no way for us to actually evaluate this, so this stays as it is. F of x sine m pi over Lx dx. Now, on this side, I'm going to be integrating an infinite number of terms here. So, this step is a little iffy in terms of being certain that we can swap our summation and our integration signs, but we are allowed to do it in this case. Lx sine of m pi on Lx dx. I really should have taken this an out for you to see, but that's okay. Alright, so this is going to be an. Now, for every value where n is not equal to m, the integration is going to be 0. Now I have an infinite number of terms from n equals 1 to infinity. One of them is going to correspond to n equals to m. In that particular case, I'm going to get L on 2. But for every other term, I'm going to be adding on 0 forever. So really, I'm left with an times L on 2. Okay? And now, just to get an by itself, and I should also say that at this point, since n is equal to m at this point, I can write sine of m pi on L as sine of n pi on L, x dx. What do I mean by that? Well, here, like we just said, the only time that this integral, because there are an infinite number of integrals, the only case in which the integral is non-zero, in fact it's equal to L on 2, the only time that that holds is when n is equal to m. So therefore I can make this m equal to n here, and every other term is going to be 0. So an is going to be equal to 2 on L, the integral from 0 to L, f of x sine of n pi over Lx dx. And so this here and this here define my solution. U of x comma t is equal to the sum from n equals 1 to infinity of an, which is defined down here, times sine of n pi on Lx times e to the negative kappa n squared pi squared on L squared times t. And that is how you solve this problem.